SMIC, or Semiconductor Manufacturing International Corporation, is China's largest contract chip maker and the world's fourth largest foundry behind TSMC, Samsung, and Global Foundries. Headquartered in Shanghai and founded in 2000, SMIC occupies a unique and precarious position in the global semiconductor industry. It is a company that has been forced to innovate through constraint, and its current strategy reveals a lot about how the chip war is actually being fought. In 2020, the United States imposed sanctions that effectively blocked SMIC from purchasing ASML's extreme ultraviolet lithography or EUV machines. These machines, which use 13.5 nanometer wavelength light, are the only tools capable of mass producing chips below 7 nanometer in a single exposure. Without them, SMIC was theoretically locked out of advanced nodes. Yet, by 2022, a teardown of a Bitcoin mining chip, the Minerva, by research firm TechInsights, confirmed that SMIC had indeed produced a functional 7 nanometer chip. The company achieved this using deep ultraviolet lithography, which relies on 193 nanometer light. The physics behind this feat is known as self-aligned quadruple patterning, or in short, SAQP. SAQP works by printing a coarser pattern, depositing sidewall spaces, then etching away the original lines to leave narrower lines behind. Repeating this process 4 times effectively shrinks a 40 nanometer feature down to roughly 7 nanometer. It is an optical trick and it works, but it comes at a staggering cost. For every single layer that TSMC can print with one exposure, SMIC must perform 4 DUV exposures with atomic level alignment accuracy required for each step. The consequence of SAQP is that SMIC's 7 nanometer process suffers from a severely low yield. Industry estimates place SMIC's 7 nanometer yield between 20 to 30% compared to TSMC's 80 to 90% yield on the same node. The reason is straightforward. Every added processing step includes particle contamination, misalignment, and residual material defects. With 4 steps replacing one, the defect density multiplies rather than adding. This low yield makes SMIC's 7 nanometer wafers economically unviable for high volume commercial application. A smartphone processor or a PC CPU requires billions of transistors working flawlessly, and defect rates at SMIC would result in unacceptably high rejection rates. Consequently, SMIC's 7 nanometer production is limited to niche, low volume applications. For example, military grade ASICs, specialized AI accelerators, and cryptocurrency mining hardware, where cost per chip is less of a concern than independence from foreign supply chains. Given the limitations of their advanced node, SMIC has made a deliberate and financially sound pivot. The company is pouring billions of dollars into expanding its production facility for mature nodes, specifically 28 nanometer, 40 nanometer, and 55 nanometer. The automotive and industrial IoT sectors are experiencing a massive chip shortage, and the chips they require are not cutting edge nodes. A typical electric vehicle contains more than 2000 silicon chips, and the vast majority of these are microcontrollers, power management ICs, and sensor processors that function perfectly on 28 nanometer or 40 nanometer processes. These chips need to be efficient, reliable, robust, and not small. And hence, SMIC can use its production facilities to manufacture these chips. On these mature nodes, SMIC's yield exceed over 90%, and their factories are running at nearly 100% utilization. According to SMIC's recent earning reports, mature nodes now account for over 75% of company's total revenue. Rather than trying to beat TSMC in a high-stakes arms for 3 nanometer or 2 nanometer, SMIC has positioned itself as the reliable, high-volume supplier of global industrial backbone. Looking forward, SMIC's roadmap for the next 3 to 5 years does not include a desperate attempt to reach 5 nanometer using DUV. Beyond 7 nanometer, SAQP hits a hard physics wall. The line width variation becomes too large, the leakage currents become catastrophic. Without EUV, 5 nanometer is theoretically impossible. Instead, SMIC is aggressively investing in advanced packaging technologies, including wafer-to-wafer hybrid bonding and chiplet integration. Eventually, SMICs can achieve the functional performance of a 5 nanometer chip using a combination of 14 nanometer and 28 nanometer dies. This bypasses the need for EUV entirely. The strategy has been championed by SMIC's co-CEO, Dr. Liang Meng Song, a former TSMC veteran. His bet is that future of chip performance lies not in lithography but in how chips are connected and packaged. In coming years, SMIC will likely continue to dominate the 28 nanometer market while quietly becoming a leader in chiplet based integration.